So few questions for the collisions, right, in the rotational motion we are going to discuss. Starting with a very simple example. Suppose this is the question when the axis of the road is fixed, right? It can rotate about this horizontal axis, right? The mass is capital M is equal to 2m, suppose, and a particle, right? A particle of mass M, right? It is coming with speed u, right? And first case, it stick with this, right? First case, after collision particle stick with rod. In the second case, after collision particle come to rest. I think we have done this question or not. Find angular velocity of rod just after collision, right? Just after collision. This is the question, right? Copy this. So we will consider this is the rod of the mass M and the length L. You can consider it is just hitting at the one end. So about this point we have to find what angular velocity just after collision. So before collision, suppose this is the point O, apply conservation of angular momentum about O, right? Why about O? Because when it will hit, the impulse is imparted at this point only. So if you are taking the angular moment about this, the net impulsive torque about this point will be 0, and therefore we can conserve the angular momentum about this point, right? So initial angular momentum and final angular momentum after collision. In the first case, after collision particle stick with the road. So in the first case, this is the particle of mass M and this is the rod of capital M whose mass is equal to 2m, and it start rotating with angular velocity omega, right? So what is the initial angular momentum about O? The initial angular momentum is mvr, m into v, right? And what is the perpendicular distance? The perpendicular distance is L, plus what is the angular momentum of the rod initially? This is 0, right? And what is the final angular momentum? Angular momentum is I omega, right? I into omega. I is mean the moment of inertia about this axis. So how to find the moment of inertia about this axis? Listen, the moment of inertia about this axis is half m 1 by 3 ml square plus this is also the mass plus ml square, right? But the mass m is equal to 2m L square ml square. So this is 5 by 3 ml square is the moment of inertia about this axis. So what is the moment of inertia? Say 5 by 3 ml square is equal to mu L. M and L will cancel out, right? 5 by 3 and this is the angular velocity, 5 by 3 m, right, u, and this is L into omega. All right. So what is the angular velocity? It is equal to 5u upon 3u upon 5L. So after collision, when the particle stick and it start rotating with this, so this is the angular velocity. Copy this. So when the particle come to rest, in the second case, when the particle come to rest after collision, right, and the collision is perfectly elastic, then what will happen in the second case, right? Second part you can write over here. Initially it is coming and after collision it acquired the angular velocity, the rod acquired the angular velocity omega, right? And this particle come to rest. So this is the m at rest and it acquire angular velocity omega. So after some time what will happen? The angular due to this angular velocity, the rod will start rotating and the particle will be at rest. So just after hitting the collision, we have to find the angular velocity. So in the second case, the conservation of angular momentum about O, again you have to apply the initial momentum is equal to final momentum. What is the initial momentum? Due to the particle, which is equal to mu into L, and the final momentum. What is the momentum of this particle? Say m into 0 plus. Only the momentum will be equal to momentum of the rod. So it will be equal to I into omega dash. So mul is equal to I 1 by 3 ml square omega dash, but the m is given as the twice of the 2ml square omega dash mul. Ml will cancel out, u is equal to 2 upon 3 l omega dash, right? So omega dash in this case is 3u upon 2l. So this is the omega dash. With the help of this, you can also find, applying the conservation of energy, how high the rod will raise its center of mass, right? Copy this. So in this question, right, there is a cube and the cube is of side 2a. What is the side? 2a. And it is fixed. It can rotate, it is placed on the horizontal axis and it can rotate about this axis, right? It can rotate. So a bullet is coming, right? And the mass of the bullet is, suppose, the m, and the speed is to be v, right? And after collision, this perpendicular distance is given as the 4a by 3, and after collision it embedded. So if this is the cube, right, so when it embedded, what will happen? The cube plus bullet system will rotate about this, and they are asking, you have to find what? You have to find the minimum velocity of this block, of this bullet, so that, this is the bullet, so that after collision, when it rotate, it can topple. It can topple mean, what is the meaning of the toppling? Toppling mean, after this it will rotate like this. Wait for 1 minute. Suppose this is the cube, right, and when it rotate about this, it rotate like this, right, and then it is toppling. So what is the condition of the toppling? Although the small mass m, the mass of the bullet is very small as compared to capital M, and this is the axis of rotation, you can assume. So when the bullet plus this cube is the center of mass, it is very small, so we can ignore after the collision, right? So after collision, what will happen? If this cube become like this, right, the center of mass, this is the m, it become like this, so it will topple on the other side. The mass m will be here, but we can ignore this mass. So this is the condition. So you can think that initially the mass was over here, then it will rotate, right, it will rotate like this, and then it will topple. You understand or not? That is the thing. Okay, so what will you apply? To solve this question, we will apply the two things: the conservation of angular momentum about this point O. Why about this point O? When the collision occurs, the impulsive impulsive torque will produce at this point O. So therefore, if we can apply the conservation of angular momentum about this point O. Is it clear? So apply conservation of momentum, conservation of angular momentum. So about O, it is at rest. What is the linear moment? What is the angular momentum of this particle? Say final. Initial is mv. And what is the final? After this, if it acquire the angular velocity omega, this is the small particle m. We can ignore this angular momentum and I into omega. So this is the angular velocity obtained. I is the moment of inertia about this axis, right? Copy this and tell me what is the moment of inertia about this. So first we will find the moment of inertia about this. Okay, so if this is the side 2a, this is the side 2a, this is the m. So what is the moment of inertia about this axis, you tell? Or listen, it is better, we have to find the moment of inertia about this axis. It is better to find the moment of inertia about this axis and this axis. What is the moment of inertia about one end? Similar to the road, ml square by 3. ml square by 3. But L is what? Say 2a square by 3. So this is 4ma square by 3. And this is also the 4ma square by 3. Right. So what is the IZ? If you assume this is the x-axis, this is the y-axis, and this is what IZ. So IZ is equal to what? Say Ix plus Iy. What is the Ix? This is the 4ma square by 3 plus 4ma square by 3. So this is equal to 8 upon 3 ma square. So this is the moment of inertia of the rod, moment of inertia about this axis. I am ignoring this mass m because the small m of the bullet is very, very small. Right. So I will put here the mv is equal to 4a by 3. The moment of inertia is 8ma square by 3 into omega. Right. 3 will cancel out, ma will cancel out, 4b upon 8a. So angular velocity is v upon 2a. So after hitting, it will start rotating in this way, I omega. Copy this. Wait for 1 minute. This is the capital M. Wait for 1 minute. This is the capital M. This is 4 small m into 8m A. So here small m into 2 capital M A. Right. Now copy this. So now we can apply the conservation of energy, because here the angular velocity omega, if after hitting it is rotated such that the center of mass reaching to the maximum height like this, right? Because it will rotate like this. So after that it will topple. So final angular velocity you can assume to be 0. So now you can apply conservation of energy. Conservation of energy. What is the energy? Say half I omega square. Their rotational kinetic energy is converted into what? Say mgh. Suppose this is the height h, mgh. Okay, distinguish between capital N and small m, otherwise the answer will be wrong. Okay, the moment of inertia we have found, it is 8 upon 3 capital M into a square, and the angular velocity is mv upon 2 capital M into a whole square. What is the mgh? You have to find this h. Listen, the initial height is equal to what? Say h1 is equal to a, and then what is this height? What is this distance? You tell. If it is a, it is a. What is this distance? It is a root 2. So the final height, it become equal to h2 is equal to a root 2. I think you understand. So what is the raise in height? So h2 minus h1 is equal to a root 2. A root 2 minus a. Right, a root 2 minus 1. Right, a root 2 minus 1. Is it clear or not? So this is 4 upon 3. The capital M will cancel out. This is a square, m is small m square, v square upon 4m square a square is equal to g into a, root 2 minus 1. With the help of this, we can find the speed v. A square will cancel out. Right. This is the 4 will also cancel out. M square upon v square upon capital M square is equal to g into a root 2 minus 1. Simplify this. 3m square upon small m square ga root 2 minus 1. So the speed is capital M small m root 3 ga root 2 minus 1. So it should be the speed. Copy this. This is the questions, right? These are the questions when the axis of rotation is fixed, right? In the previous question, the rod was also fixed, can rotate about the fixed axis. Now we will do some questions if the rotation of axis is not fixed and the body is free to rotate, right? For example, suppose there is a rod, right? And the rod has the mass m and the length L, right? This is the length L. Is it clear? So now a particle is moving of the mass m and the speed v like this, and this rod is free to move on smooth horizontal plane, smooth horizontal plane, right? Like this. Okay, copy this. I have sent you the photograph, the first photograph, right? This is the question number 21. Can you read the question, please?
Yes, sir.
Read the question.
The uniform rod of mass m and length a is on a smooth horizontal plane. A particle of mass m moving at a speed v perpendicular to the length of the rod strikes it at a distance a by 4 from the center and stops after the collision. Find the velocity of pitch of the rod and the angular velocity of the rod about its center just after the collision.
Okay. Okay, so in this question, a rod is free to move and the particle is, this is the length L, right? I'm assuming this is the length L, and the particle is moving in the same plane, right? The mass m and with the speed v. And after collision, particle stops, right? Particle stop. So what we have to find, although this distance is given as the L by 4, right? After collision, particle stop. Find first the velocity of center of mass of rod. You have to find the velocity of center of mass of rod just after collision. Second, angular velocity, angular velocity omega, right? You have to find just after collision, just after collision. This is the question. So what will happen? You tell me. What will happen when it is coming? It will stop. It will stop with respect to center of mass of the rod. So rod will acquire some some velocity of the center of mass. Also, it will start rotating like this. So after some time, the situation will be like this. It will start rotating, right? Like this. It will start rotating like this. The center of mass will be at this point. It will be moving with some velocity of the center of mass. Also, it is rotating with some angular velocity omega. So you have to find this such that the particle stop, right? Copy this. So you tell me, if you consider the rod plus this particle system, what is the external force on this system in the x direction, right? You tell me. I'm writing from here, right? No external force in the x direction. Are you getting or not? If no external force in x direction, so momentum is conserved in x direction. Is it clear or not? Therefore, the initial momentum and the final momentum in x direction both are same. So before collision, you tell me, before collision, what is the linear momentum? Say mv, because the rod is at rest. After collision, the particle come to the rest. It is at rest. But the center of mass, which is of the capital M, it start moving. So what is the final momentum? This is the initial photo. This is the final photo. It rest. So its velocity is 0. No momentum acquired by this. M into VCM. M into VCM. Is it clear or not? So they are asking the velocity of the center of mass of the rod. So what is the velocity of the center of mass of the rod? mv upon capital M. Is it clear or not? Also in the second part, they are asking the angular velocity omega. To find the angular velocity omega, right? To find the angular velocity omega, what you have to do? It start rotating like this. What is the angular velocity omega? How to find? Applying the conservation of angular momentum, right? Apply the conservation of angular momentum about this. For example, it is start rotating omega about this point O. So conservation of angular momentum, right, about center of mass, right? About center of mass. So initial momentum and final momentum both are same. So initially only this is rotating, this is moving, mvr. So m into v into r, what is r? Say L by 4. After this, it is at rest, so no angular momentum, but this rod start moving. So I have discussed the angular momentum in case of CTRM, right? So what is the angular momentum of this rod rotating with omega, and the velocity of the center of mass is VCM. So about this point O, what is the angular momentum of the rod? MVR. But what is the R? Because this mass M is passing through this point, so R is 0 plus, right, I into omega, right? What is I? I is the moment of inertia, say ml square by 12 into omega, and mvl by 4. So small m and capital M are different. mv, L will cancel out, L by 4, ml by 3 omega. So omega is 3 mv upon capital M into L. So this is the angular velocity of the rod after which it rotates, and this is the velocity of the center of mass after which it will rotate. All right, copy this. So we are doing the same question, same type of question the previously we have done. Suppose we have a rod AB, right? This is the rod A and this is the rod B. The mass supposed to be the L, mass M is the length L, right? It is placed on the horizontal frictionless surface, right? The mass M with velocity v naught is traveling, right? If collision is perfectly collision between this point, right, particle of hit the end A, so I am assuming this is the A and this is the B, no problem. If collision is perfectly elastic and particle come to rest, particle comes to rest, you understand? That is the thing. Find first the ratio m by m, you have to find the B, right? Point P on the rod AB, you have to find the position of point P on the rod AB, which is at rest, just after collision. Find C part, linear speed of the point P. This is the point P which is at rest, linear speed of P after time pi L upon 3V naught. This is the time. Is it clear or not? Copy this. So now let's see how to solve this question. Right, it come to rest after collision. The same thing we will apply first for solving the first part, right? We will apply the conservation of linear momentum, right? So linear momentum, because if you consider this the system, particle plus rod, no external force is applied, so therefore initial momentum and the final linear momentum is same. After collision, listen, after collision it come to rest and it will start rotating. So what will happen? You tell, it acquires some angular velocity omega, no doubt. Also this particle come at rest, right? It is at rest. Also the velocity of center of mass is achieved. The same thing we will apply. The initial momentum of the system is m into v only, and what is the final momentum? Say m into VCM. So what is the velocity of the center of mass? mv naught upon capital M. This is the one thing. Conservation of linear momentum, right? The another thing of the angular momentum, right? What is the angular momentum, you tell? If the rod is L and it hits the end A, this distance is what? Say L by 2. about the center of mass, you can conserve the angular momentum. Although this is free to rotate and no external impulse or anything is applied, you can apply the conservation of angular momentum about any point, right? But it is better to write the conservation momentum, apply conservation of angular momentum about center of mass. Is it clear or not? So apply conservation of angular momentum about center of mass. Initial angular momentum, final angular momentum. About center of mass, it is coming with mv naught into L by 2. What is the final angular momentum? Say half I into omega. What is the moment of inertia? ml square by 3, ml square by 12, mv naught L by 2. This is 6 m small m v naught by 2 m L, right? I ml omega. So angular velocity is 6 m v naught upon capital M. So this is the VCM, this is the omega. First copy this. Collision is perfectly elastic. Okay, so now the collision is perfectly elastic. What we have to apply? The conservation of energy. Apply conservation of energy. What is the initial energy? Say half m v naught square is equal to what? The final kinetic final energy. It is at rest. It does not have any energy. So it is the energy. It is doing the CTRM. VCM is also there and the angular velocity is of there. So if this is the capital M, so what is its energy? Half m VCM square. Also it is performing the rotation motion, I omega square, right? Half m VCM. What is the VCM value? Small m v naught upon capital M whole square. What is the moment of inertia about center of mass? And what is the angular velocity? Capital M into L. So half m v naught square, right? Half I, wait for 1 minute. The energy, rotation energy is half I omega square. So this is the half, this is the half I omega square, right? You will see the v naught square, v naught square, v naught square will cancel out. So it is also the 1 by 2, 1 by 2, 1 by 2 will cancel out. So this side is m, right? Capital M square upon capital M square plus m, L square and L square will cancel out. M by 12, 36 m square upon capital M square, right? So small m is equal to small m upon capital M plus Bharatiya 36 small m upon capital M. Multiply by this is the m square, right? 1 m will also cancel out. M upon capital M plus 3 small m upon capital M is equal to 4 small m upon capital M. So the ratio they are asking, right, it is equal to 1 by 4 small m upon capital M. The small m upon capital M is equal to 1 by 4. This is the answer. Copy this.